So the next is thermocouples. The stuff for RTDs is a little bit simpler. So the next step is thermocouples. It's a little bit more complicated, and this is mostly caused of the temperature range, because with the increasing of temperature, the problems increase minimum by the power of 2, mostly by the power of 4 to 5. And this is unfortunately the case, but it's also a kind of challenge to face it. This is a small selection of thermocouples used in the middle, for example, power stations, the angle type in molten metal applications, molten iron, the ones with a green wire, and also they are in the horizontal shape, mostly automotive applications. The lower left-hand corner is typical elements for plastic machines, plastic molding machines, and so on. Above on the left side are sensing elements, temperature sensors for the fuel for motors in ships. They are mostly fired with natural oil, and so you must heat the natural oil to minimum 250 degrees before it is liquid enough to pump in the motor. So these are these sensing elements, and mostly are used type J thermocouples for it. Yes, motors 10,000 kilowatts and above. Yes, so when you stand there, the cylinder head is in the 3rd floor. Okay. Okay, we are now in the field of changing in thermoelectric properties. And we have also quite a nice selection of subdivided themes we have to follow. Basically, thermoelectricity, Seebeck effect, Peltier effect, Thomson effect, all have an effect in temperature measurement with such elements. And unfortunately, they are combined together. So you cannot have only a simple effect, but you have always a combination of all the Seebeck, Peltier, and Thomson effect. The consideration of the following part puts the application of thermodynamic principle into the center point of view and demonstrates the conversion of heat into electricity or electrical energy, and conversely. Generation of electricity and temperature is combined together, and it is not divorceable in no kind. Whenever you transport electrical energy, you synchronously transport heat energy. And when you transport heat energy, you always transport also electrical energy in a metallic conductor. Always. It is not possible to divorce these two effects and take it apart. It is not possible. So the difference in temperature are often measured as thermal EMF. Conversely, thermal EMF is often a cumbersome source of uncertainty in precision measurements. As closer you come in precise measurement to 0 volts or 0 millivolts, as higher is the probability that you are disturbed by thermoelectric effects between the wire connected to your terminal, 2 terminals, and the temperature difference between the 2 terminals. The cold air stream of an air conditioner can disturb your measurements by up to 40 microvolts, and 40 microvolts at a thermocouple type S is the equivalent of nearly 3.5 degrees. So, unfortunately, it is. To eliminate or even minimize these systematic errors, a good knowledge about thermoelectric effects is unfortunately necessary. And I try to fill your brain accordingly. The Joule effect. Everybody knows a conductor is heated up due to the current which passes its ohmic resistance. This is the source of the self-heating effect of RTDs. Yes? The heat quantity is the result of the multiplication of I squared times R. Square the current times the resistance. So the resistance in this equation is linear, while the current is in the second order. The Seebeck effect. A DC voltage is produced in a current loop of two dissimilar metals if the two junctions are held at different temperatures. This is the absolute main expression for measuring with thermocouples. You do not measure the temperature, you only measure the temperature difference between the hot side of the thermocouple and its cold side. Only the difference. Nothing else. Anyway, nothing else. The Peltier effect. If a DC current flows through a loop of two different metals, then one of the two junctions is cooled, which are connected in line. Yes, and so the sum of the current produced by each of the differential small thermocouples is added to the complete result. It's only a model for thinking about. Otherwise, it is not easy to understand why you can measure in a gradient. And you need a gradient. You need a difference between the hot side and the cold side. Yes, and I explain it later on where the current is produced. It is the current is definitely not produced in the hot side, in the tip. Definitely not. Because this is not possible. We are in the DC world. We are in the DC world, and the ohmic law is still present and in charge. And so when you have no resistance because of the short circuit, it is not possible to have a current or an EMF. So the EMF or the current from a thermocouple is produced somewhere else, but not in the tip. And basically it is produced in the area where the temperature changes. And physically it is not other possible. When I have this piece, it has a different energy level related to the ground. But we cannot use it because it is in a stable condition. Only when it falls down. In this moment I can use it, but only for the time between the stable condition here and the stable condition there. Only in that time. It's the same principle for a thermocouple. Only where the temperature changes, the current is produced. We come later on. Okay. The polarity of the thermal EMF, or the current, let's take the synonym EMF for further discussion, is dependent on the gradient and its direction. With a thermocouple, you can produce positive and negative EMF. It's depending on the gradient and the direction of the gradient. additional inserted areas of higher temperature has no effect on the result because the EMF generated compensates each one another. The total amount of EMF which is generated is only proportional to the temperature difference, unaffected by the temperature profile in between. Even in the right, where you have higher and lower, you have peaks and soaks in between, typical for vacuum furnace applications, for example. The total amount, the output, is exactly the same as in the left graphic, if the temperature difference is constant.
What he means is that the output EMF will be same in all the conditions. It depends on only the hot junction and the cold junction. Whatever happens in between, for example, T1 is at 1000, T2 is at 20. In the third case, if we see, the temperature goes over 1000 degrees in between. So after the hot junction, even if the temperature goes above 1000 degrees centigrade or somewhere it goes below 20 degrees centigrade, then also the output would be similar. So it does not matter what is happening in between, but what matters is between the hot junction and the cold junction.
No, but if we consider the instantaneous position in third diagram,
yes,
then at peak of that diagram,
yes,
the T1 would not be the same as we considered over here.
No, if you see the hot junction and the cold junction, hot junction is at 1000, but somewhere after the hot junction, it goes over 1000 degrees, and somewhere before the cold junction, it goes below 20 degrees centigrade. Then what he told in the first diagram was it is a sum of many thermocouples put together.
Yeah.
So there was an addition here, but there was a deletion because the temperature came down. So overall, the voltage produced, EMF produced, will be the difference between this hot junction and the cold junction. It will be proportional to that.
A positive gradient produces a positive EMF and a negative gradient produces a negative EMF, so this is compensated. Theoretically it is totally compensated, practically not. We are in the real world, we are not in the theoretical world. Yes. So, but this is the case. Yes. For example, consider a high vacuum furnace. Yes. You have your charge in the middle, and you try or you like to have the temperature of the charge measurement. But between the cold world outside, the probably water-cooled wall, you have shields inside, protection shields. And basically you have to go through the shell of the heating element. Yes, probably a molybdenum heater or a graphite heater. So there is the temperature definitely much higher than in the charge and in the wall, in the water-cooled wall. But it is possible to measure the charge temperature because of the EMF. The polarity of the EMF is defined by the direction of the gradient. Positive gradient produces EMF, and the negative gradient reduces the EMF. Yes, and therefore it is possible to measure.
That is why it is important to have a uniform thermocouple element throughout the length of the thermocouple. You cannot have the composition only in the hot part and the rest can be normal. So it has to be, a thermocouple element has to be uniform throughout the length. Second thing is, the thermocouple will not end at the head. So you have to use an extension, compensating, or a thermocouple cable to your apparatus, which is measuring the temperature, where you can do the cold junction compensation. That's the basic thing.
All the hardware between the hot tip and the input terminals of your measuring device meter or transmitter have an effect on the temperature measurement with thermocouples. All between, cable included. And again, what you measure is only the temperature difference between your reference junction or your cold junction and the hot tip. Nothing else.
You need to know the cold temperature as well to know the actual temperature.
Well, as a refraction of this, the thermal EMF in a homogeneous temperature area is 0. No temperature difference, no EMF.
To keep that thermocouple in room temperature, you will measure 0 voltage. So both are at the same temperature. You can only find the EMF when you put it in the hot.
Yes, the thermal EMF of a TC is exclusively a function of the temperature difference, nothing else. The resulting thermal EMF in a thermal circuit of any number of different materials is 0 when all components are on the same temperature. Homogeneous TCs or pin connectors made from different materials are in sum without an effect as long as there is no temperature difference. Practically, adverses. Practically, we have to live day by day with different temperatures. Yes, this is our normal working day. We always deal with different temperatures. In no case the input terminals of your transmitter have the same temperature as the wire between. In no case. That's it. That's life. So only under theoretical either thermal conditions you have no effects. But our daily work is to fight against such effects day by day when we use thermocouples. And as I explained before, resistant thermometers is not always the solution. Okay. Inhomogeneity, this is the base of what is written there. Inhomogeneity causes errors. The inhomogeneity can be material inhomogeneities, can be inhomogeneities between the thermocouple and the connecting wire, inhomogeneities between the connecting wire and the material of your input terminal. All these are inhomogeneities, and all these points cause thermoelectric effects. And the knowledge about this and to take this in consideration helps you to measure with a thermocouple the correct temperature, or temperature difference, basically. Only circuits comprising of dissimilar metals will generate a thermal EMF. The output will be produced only when a temperature difference or a gradient exists. For accurate and stable operation, the thermoelectric characteristic of the conductors must remain constant throughout and homogeneous. This is not possible, so we have to live with mistakes. And we have to take in consideration the mistakes, and we give them a number to have an idea what is the effect and how high is the effect. Tomorrow in the morning, I fill your brain with uncertainties, I tell you. It will be a nice morning. Okay. This is what I explained before for a thermocouple type J, an iron wire and a copper nickel wire. One is heated up to 200 degrees, the other to 0 degrees. If you take it really apart, you put in a compass, you will find a deflection. But this is not practical for our daily work. So we have to open the circuit and connect it to a meter. Unfortunately, the meter inside has copper wires. So it's a different material from that what is in the outside world. So we cannot expect that the indication is correct because of the different materials at a different temperature between the two sides. So we have to do something. We can make the thermocouple longer by using the same or equivalent material, means extension or compensating wire. Yes, but it does not help us for the effect that the indication of the meter due to the copper wires is erroneous. So what we have to do is either we can mechanically adjust the meter. If we have 20 degrees on the measuring point and we have 20 degrees at the input of the meter, then the output is 0 because no temperature difference. So we can use a screwdriver and adjust the meter to 20 degrees and not to 0, because the temperature is not 0, it is 20 degrees. Yes, this is one point, it's mechanical. Or the other way is we use a reference junction, a reference temperature. Yes, and due to practical reasons, the reference temperature is per definition set to 0 degrees centigrade, means ice in water. Demineralized water in ice made from demineralized water in demineralized water. Yes, this is practically 0 degree. When you use trap water here in this area, this is somewhere around minus 20 millikelvin below 0 when you use the normal water which you get from the water supply and trap water. And for thermocouple measurement, a difference between 0 and minus 20 millikelvin below 0. This is, in Germany we have an expression for it. I cannot translate it in English. My education does not allow it. Yes, so what you have to do is you bring your thermocouple or the extension cable to a point where you put it into ice water, and then you can go with copper cables from this point to transport the electrical energy to your meter for measurement. One of or two or more of the audience may be in calibration laboratories. I think the use of the ice pot is very useful and very common to them. They do it day by day. We also did it mostly in the laboratory, and we always had ice in the fridge, so we did it day by day.
8 to 10 people are from the lab.
I saw nobody making something like this, or in India.
Not all laboratories are using
Yeah.
the ice point.
Okay. These ones who do not use an ice point, they use an electrical or electronic compensation. So what you also can do is you can measure the temperature at your input. Normally it is constructed quite massive with a metal behind, and you measure this, what is called an isothermal block. You measure the temperature, you amplify the signal and add it to the input in microvolts, and then you bring it to linearization. The second way is the more modern way is you have a reference sensor on the isothermal block, and you have a second loop in your microprocessor controlled meter. This is mostly the way. Okay. Thank you, as so far, for your patience in listening to me. Thank you very much.
If there's any question you can ask now.
Sorry?
Injection compensation.
Yes, it's cool joint compensation. Yes, yes. All the EMF tables in the standard are referenced to 0 degrees centigrade, means to the ice point, and not to the water triple point. I don't know why, but okay, I feel you. Okay, we proceed on with the theory of thermocouples. The question is, how can you imagine what two elements, dissimilar elements, form a thermocouple, and what will they produce for an output? So for the producer of thermocouples or the thermocouple material, it is quite essential to know it. And when you look on the table, then you see that a reference material, it was recommended 1968 by the NBS, National Bureau of Standards. Now it is called National Institute for Standard and Technology in Washington, US. It is a special kind of a platinum material or platinum wire with specific impurities. And this material is used to measure the Seebeck coefficient for the different alloys. When you, for example, look in the left-hand column, the second from above, copper-nickel, it forms, when you use it as a thermocouple against this platinum 68 wire, it produces minus 35 microvolts per Kelvin. And when you go to the middle column, in the middle you see copper. Copper forms 6.5 plus 6.5 microvolts per Kelvin by using this platinum 68 wire. So if you combine the nickel copper, the copper nickel and the copper wire to form a thermocouple, you simply add the two values unaffected by the pre-sign, and you find that it is about 41.5 microvolts per Kelvin. And when you look into the table in the 60584 international standard from IEC, you will find that the average increase or the average coefficient for a type T thermocouple is approximately 41.5 microvolts per Kelvin. It is not constant. The temperature relationship and EMF for thermocouples is highly nonlinear, also in small temperature ranges. More common is to look at what is written in red, nickel and nickel chromium. Everybody knows nickel chrome nickel is type K thermocouple, the outmost used thermocouple in industrial applications. And you see nickel chromium produces 25 microvolts, nickel produces 15, so 40 microvolts is approximately the average Seebeck coefficient for a nickel chromium nickel. You know, 1,000 degrees produces 41,240 microvolts. Okay, so this is a matter of fact. When you look into the right column, in the lower part you see some, let's say, strange elements which produces very high EMFs against platinum. And when you see the highlighted in yellow silicon, you see 440 microvolts per Kelvin. This is an incredible high number. So you can imagine that even small amounts of silicon in a noble metal thermocouple will produce highly erroneous measurements. You can take in account that approximately 1 ppm silicon in a noble metal thermocouple produce an error equivalent to half a degree centigrade, even 1 degree. So for noble metal thermocouples, you must carefully both protect it and handle it when you have the bare wires. You cannot touch them with plain fingers because the sweat on your skin always contains silicon. Silicon is the most common element in our ambient on the Earth, more than hydrogen. So it is all over where we are. Everything is silicon content in some kind. So when you handle bare wires, bare noble metal wires, you have to take it in a clean ambient, protective gloves, dust-free atmosphere, and so on. It's essential. And when you put it in an industrial environment, you must carefully look on the environment and to protect the thermocouple from influences, especially from silicon. Okay? So if you make a graph from the Seebeck coefficient over the temperature, then you probably will notice that there are 4 groups. The upper 5 lines, or even 6 lines, the upper 6 lines are the non-noble metal thermocouples. And you see that the relationship between temperature and EMF is highly nonlinear. Yes? So the lowest 3 lines are the noble metal thermocouples, S, R, and B. The advantage is they have a higher using temperature. The disadvantage is they have a low thermal output. The low
Microvolt per degree centigrade.
Sorry?
This is microvolt per degree centigrade.
This is microvolts per degree centigrade, or microvolts per Kelvin. Yes? So, in the middle, there are 2 which come straight outside the lower 2 groups. These are quite new elements. They are formed from a gold-platinum wire or from a platinum-palladium wire. And both of the wires are pure elements. They are not alloyed. And so you can see that especially the gold-platinum wire or the gold-platinum thermocouple is quite linear. And this makes it very advantageous for precise measurements. But they have a different standard. It's in the 50,000 group and not in the 60,000 group. And they are very good, very reliable, extremely stable, good sensitivity, but for industrial use they are not suitable. In no case. The drift rate is very low, but they are very sensitive to contamination. So outside a laboratory environment, it is nearly impossible to use them. And especially the platinum palladium, it can be used up to 1500 degrees, but the palladium makes the platinum wire very coarse grain, and so it is sensitive to vibration. You must handle it with care. In my previous laboratory, we had both. We had a gold platinum and a platinum palladium calibrated at the National Meteorological Institute in Germany with uncertainties down to 300 millikelvin for temperatures of 1000 degrees and above. So this is not achievable with others. With type S, you will not get it, such figures. So the last group are the refractory elements. They have the highest temperature for use. They have a medium EMF generation, and they are not very linear, but they are constantly bent. These are the refractory types, C, D, and G, where the type G, where one leg is a pure tungsten wire, is not longer used. The type C and D, these are the both types which are commonly used, where type D is considered to be less stable than type C, and so type C is in the newest edition of the 60584 standard included, as well as the type A. It is a Russian standard, from a GOS standard, and this one is maybe used up to 2,500 degrees centigrade, and it's quite stable, but for all refractory elements, take in consideration that the uncertainty is near to 1% of reading. We seldom found wire combinations which are, let's say, half of it, 0.5%. And anyway, in the first heating cycle, there is a recrystallization effect. Basically, all thermocouples which are alloys have a recrystallization effect, all of it. So when it is produced by Tempsens and you measure it in the laboratory, you will never find the same figures. They are always slightly small but different. This is due to recrystallization processes between the manufacturing process and the calibration process. Temperatures are different, profiles of the furnaces are different, and so you will never find exactly the same amount of microvolts. If so, you should think about mistakes because the probability that you will find exactly the same figures is very low. Below 68.4%, I can tell you. Yes, so there are always differences. And we did in our previous calibration laboratory, we did about 4,000 calibrations per year, mostly non-noble metal thermocouples. And when you calibrate and you look on the result, on the behavior of a thermocouple, over the time you have the experience, you look at it and say, okay, this is Tempsens material, this is isomil material, this is ABB material. The manufacturing processes are different, and they have definitely an influence on the behavior of the thermocouple. Yes? So also Okazaki material, for example, you can identify it, where it comes from. And the difference are small, but they are. They are at noble metal thermocouples, they are at non-noble metal, and they are at refractory thermocouples, maybe quite high. Okay. There are also German standards or European standards available, as well as IAC, this is the international standard, and ANSI, this is the American standard. And beyond a huge number of possible metal combinations which may form a thermocouple, only a small number was selected and was standardized. Basically, there are only 5 non-noble metal thermocouples, 3 noble metal thermocouples, and 2 refractories. And that's it. Not more. And selected were material combinations due to partly historical, practical, technical, or metallurgical reasons. Beyond the non-noble metal thermocouples, only one was developed by using special special combinations and alloys. Only one, type N. All others were standardized because they were still existing and widely used. Yes, you know, there are some fundamental laws in measurement. One of it, we always did it in this way, and the second one is we never did it in another way. So these are fundamental laws in measurement. I see a smiling all over, so everybody knows these two fundamental laws by its own experience. Thank you. So this was the reason to standardize this thermocouple, with all their disadvantages and obviously also disadvantages. So only type N was developed somewhere around 1965 by an English-Australian laboratory, and afterwards it was 1969 firstly incorporated in a circular from the NBS, and then it was standardized. Especially the thermal EMF table and the permitted deviations are standardized and not the precise metallurgical combination in percent. This is important. So what the manufacturers do is they have an alloy of nickel chromium in 1.5 or even 2.5 tons, and they have 1.5 or even 2.5 ton nickel. But it is industrialized produced nickel and nickel chromium. So there are impurities inside. So what they do, they make what is called ingots. Something like this. They take a sample from it, the nickel and the nickel chromium, and they measure it against platinum 68. Yes? And then they find, okay, this does not form class 1. So one of the components is melted up again, and by putting in some ingredients, small amounts of ingredients, they shift a little bit the Seebeck coefficient so that the combination forms a thermocouple type K, type J, type T, type E. This is practically, and this they do in this way, really. So therefore the alloy itself is not standardized except type N. Type N, the alloy is standardized. You can have a look in the table and you'll find the figures in percent for the alloy. And it causes us a lot of work to have these combinations inside. So this is also valid for the noble metal thermocouples. They do it accordingly. They vary. No, they do not make impurities in the platinum wire, but they vary by refractions of percentage the content of rhodium to form a thermocouple class 1. So these are the thermocouples which are standardized as so far. J, T, K, E, N as the non-noble metal thermocouples, S, R, and B as the noble ones, and C and A as the refractory ones. Sorry?
This is same in IEC as well as ASC.
Yes. The non-noble metal and the noble metal, they are named in the ASTM E230, and C and D is nominated in the ASTM 988, and the A is nominated in GOST 8585. So probably somebody could ask why platinum rhodium 10% against platinum and platinum rhodium 13% against platinum is available. On the first side, it makes no sense. Yes?
But there is difference in the application where the microvolts that is being produced.
Yeah, but the difference is quite small. Yes? There are two major reasons. One reason is before World War II, it was not possible to produce really pure platinum. So the thermocouple named S, a platin-rhodium against platinum, was characterized in the IPTS from 1927. So after the World War II, they found that now they could produce platinum more with less impurities, and when they use it, they cannot form a type S thermocouple with the same characteristics. So what they did is they renamed the type S to type R for the same characteristic by using 13% rhodium in the platinum, and the former type S now with the more purity wires are named type S. This is one of the reasons. The second reason is that the platinum 10% wire is under-atactic alloy. Means you could have more rhodium in the platinum to cover all free positions in the crystalline structure. About 11.2% are necessary. So anyway, there are free positions in the crystalline structure which easily can covered by strange elements, contamination, silicon, and of course also rhodium. So the stability of a type S is less than compared with a type R, because type R is over-atactic, the alloy. So there is there is always enough rhodium to cover all free positions in the crystalline structure. An addition is that the movability of rhodium in platinum is about 5 times higher than the platinum itself. So rhodium can easily remove or move inside the platinum wire where free positions are. So depending on the temperature gradient in your furnace and the speed of heating up and cooling down, the rhodium moves, and this causes inhomogeneities and drift effects in the platinum-rhodium thermocouple type S. This effect is much less in type R. So most of the laboratories, for their standards, they use now type R thermocouples instead of type S because of higher stability and less problems with inhomogeneities. Even better is type B, because both legs are alloys. This stability is much higher, but type B is not available in class 1. It's only available in class 2, even not at incredible high prices. Okay. So,
for industries also it is suggested to go for type R in place of type S.
yes, stability is better, and the problems with inhomogeneities is lower. It is better. Unfortunately, the price is slightly higher because rhodium is, in most cases, higher in price than platinum. And so 3% more causes a higher price. Yes? But if you have a highly sophisticated production system, and when it stands for maintenance 1 hour and it costs $10,000 this 1 hour, then you should carefully think about if probably $50 more in a thermocouple is more efficient than $1,000 to pay for maintenance 1 hour. That's something we should take in consideration. For type J, it's a little bit seldom. The ASTM E230 gives tables for type J up to 1200 degrees. But due to intercrystallation effects, especially in the iron lag, there are instabilities and hysteresis somewhere around 760 degrees. And therefore we added in the standard a recommendation not to use a type J thermocouple at temperatures above 750 degrees. Unfortunately, the permission to use a car in California, the outlet temperatures from the car are measured with a type J thermocouple, and the outlet temperatures before the catalysts are somewhere around 1000 degrees for a gasoline. And it is a silly situation, but since today the system in California is to measure with a type J thermocouple the outlet temperature of a gasoline engine. Silly but true. Yeah, but this is America. You cannot expect something else. Okay, so we come to the noble metal types. You can use them practically up to 1768 degrees, which is the melting point of platinum. Yes, both of it. It is recommended not to use them above 1600 degrees, and but it's especially to the user how to do it. The type B can be used at higher temperatures, and the advantage for the type B is up to ambient temperatures of 50 degrees, it does not use extension wire or compensating wire. It needs no cool joint compensation. When you have a graphical display of the EMF in the range between 0 and 50 degrees, you will find that it is only in the range of plus minus 1 microvolt. And so this makes it possible that no compensating wire is needed for this, as long as you can hold your cool joint or your temperature where the copper wire to the platinum rhodium wires are connected. You can keep this point below 50 degrees centigrade. In a power station it is nearly impossible, because power station you have, even in Germany, ambient temperatures of 55 degrees and above. So there it is not possible. And there are compensating wires available, but they are quite expensive. Okay. Oh, sorry. Okay, the two thermocouple combinations highlighted in red are now newly in the IEC 60584, and So they can be used for type A and type C. By nomination, the positive leg is the same, has the same alloy combination, but practically you cannot interchange them. Yes, the type A is recommended or can be used up to 2,500 degrees, and the type C up to 2,315. But you must take in consideration that both thermocouples show a recrystallization effect at reaches above 1,250 degrees. So after the first 1 or 2 heating cycles, you may find that the permitted deviation is outside the 1%. We often found it. It is not because the manufacturer is unable to produce quality material. It is a metallurgical effect. The tungsten rhenium types are the only types under all thermocouples which are nearly immune against hydrogen or hydrocarbons. Anyway, if you have a process with higher temperatures and hydrocarbons or hydrogen in the atmosphere, you have no other choice than using a refractory element. In an hydrogen-containing atmosphere, the lifetime of a noble metal thermocouples is counted in weeks, even hours. You know, as a sales engineer, I would always recommend noble metal. Okay, forget it. The other side is refractory elements may never be used in oxidizing atmospheres, under no circumstances. 450 is really the out maximum. At higher temperatures, please be careful, the tungsten rhenium wire can burn, and the burning temperature is somewhat around 3,500 degrees. So this is really dangerous. And so the positive leg has a color, while the negative leg in any case is white. And for cables, the outer insulation complies with the color of the positive leg. Until omega comes, omega, only the compensating wire follow this scheme. The extension wires have always a brown outer color. But this is omega. So from the color of the wire, you can consider on the type of the element, and from the inner colors, you can consider which is the positive and which is the negative leg. There was over many, many years a difference between the European scheme and the American scheme. Yes, in ASTM, the positive leg is yellow and the negative leg is red for a thermocouple type K. In Europe, historically, the positive leg is red and the negative leg is green. So a technician comes and says, oh, red and yellow, red and green, okay, red to red. And unfortunately, this causes about 17 degrees mistake. Okay, now we have this situation not any longer, but it comes to silly situations that sometimes you follow with the cable the international color code, and the pin connector is in the ASTM them color code, so you have a green wire and a yellow pin connector. Okay, that's life. There are a number of other thermocouples which are sometimes used, very seldom, extremely high prices, but they are used. Platinum 2, for example, is a precious metal thermocouple with high stability and less drift effects, and it has exactly the same characteristics as type K elements. So without reprogramming your transmitter or your measuring instrument, you can interchange a type K to a platinum 2. But it is a noble metal thermocouple. Yes. The KP means it is from a thermocouple type K, the positive leg, which is used against a gold iron leg for extremely low temperatures. Platinum molybdenum is sometimes used when you have very long thermocouples vertically installed at high temperatures because the strength is higher. The platinum 40 rhodium is the only one which you can use at high temperatures in oxidizing atmospheres. Together with the iridium 40, it is the thermocouple with the highest using temperature in oxidizing atmospheres. Okay, the two lower ones I have mentioned. Nickel molybdenum, nickel is used for vacuum because the possibility to store hydrogen in the crystalline structure is very low at this thermocouple type, and so it is sometimes used in vacuum atmospheres. From my knowledge, the only producer of such material is Carpenter in US. It is called Carpenter 40. Accuracy. Accuracy is my hobby. Most of the thermocouples are available in class 1 and class 2. And for the negative range, below 0 degree, there is class 3. And you see that class 2 is somewhat around double of class 1, the permitted deviation. And the permitted deviation means in a certain range you have a constant permitted deviation of 1 or 1.5 degree centigrade, and after a break point you have a multiplying factor to it. So this means whatever is bigger, plus minus 1.5 degree, for example class 1 for a thermocouple type K, or for 0.004 times temperature, or the absolute value of temperature in degrees centigrade, whichever is bigger. So if you divide 1.5 or 1.5 divided by 0.004, then the result is 375. So in the range from minus 40 to plus 375 degrees centigrade, you have a constant permitted deviation of 1.5 degree. And above this, you have a multiplying factor which comes out to 4 degrees at 1,000 degrees, obviously. Okay? Newly in the standards is mentioned that for cyrogenic applications, class 3 material does not necessarily comply above 0 degree to class 1 or class 2. And vice versa, class 1 or class 2 degree, class 1 or class 2 material must not comply with class 3 at low cryogenic temperatures. This is by variation of the alloy is done. So normally if you like to have material which is the same permitted deviation at -100 as well as +500, you must tell it prior to the vendor and he must select the material accordingly, which is highly costly.
Class 3 is mainly for negative temperature.
Yes, yes. For example, for type K and type N, it is only for the range from -200. There is a mistake. It must mention +40. Only in that range. Class 3 is defined. And above -40, it must not complain with class 1 or 2. Mostly it is outside. Okay, and for type B material, class 1 is normally not available, even not against high price adders. So class 2 is the normal quality, and class 3 sometimes is available. But class 3 is only for the range 600 to 1700 degrees. This is a graphical display about the uncertainties over the temperature for the different types of thermocouples. And it is only the positive side. As PT100, it is mirrored on the negative side accordingly. Basically, the AWG number of the thermocouple wire has no effect on the generation of EMF. To use different sizes is only a question of strength and stability at elevated temperatures. For example, a noble metal thermocouple of 0.25 millimeter in diameter, the upper line in the table, if you mount it vertically, the maximum length is ½ meter. If it is longer at higher temperatures, it will disconnect by its own weight. If you have a 2 meter long noble metal thermocouple, for example, to measure the upper temperature in the boiler house, typically the elements are 1750 millimeters long, sometimes longer. At least you need a thermocouple wire of 0.5 millimeter for noble metal and 1.6 millimeter for non-noble metal thermocouples. The wire sizes are mostly international, also international, given in millimeters. So sometimes the AWG number is in bracket because it is not exactly the same dimension. So this is a table for the different color coding, which was also previously used in Europe, and sometimes in older installations you find the old color coding still today. For some selected customers, my previous company still has in stock a cable from the old color coding, but now it runs short. You see, the main difference is between the MC96-1 and the 60584-3. And in the column, the first column, iron, copper, nickel type L is a German specialty. It has the same alloy as type J, but a different characteristic. The difference is somewhere around 5 Kelvin per 100 degrees centigrade. It's not known outside Germany. It is not known and not used. Okay? The tungsten uranium thermocouples. Finally, maximum user temperatures 2,500, maximum 2,300 to 2,500, and there are some slightly differences in the color coding, but now in the international standard it is now red for the positive wire and white for the negative leg. Those have the same color. They are ideal for applications with reducing atmospheres. And inert atmospheres, obviously, and vacuum is also possible, but for reducing atmospheres, this is the only solution. They may not used under no circumstances in atmospheres containing oxygen or water. They have a moderate stability at temperatures up to 2,000 degrees and above after the first 2 heating cycles, when recrystallization effects come to a stable condition. The CMF is approximately 20 microvolts per Kelvin. It's half of that from a type K, but the accuracy, the guaranteed accuracy is mostly not less than 1%. 1% of reading. Needs always protection against process environment. It's always needed. Bare thermocouple wires you can only use in high vacuum furnaces. Extremely rigid and brittle material, and the price is comparable to noble metal thermocouples. But at high temperatures, you have no other choice. It's not easy to handle, especially when they once warmed up, and so special cautions must be taken care when forming the hot tip, the welding tip. A disadvantage is that the 2 legs of the refractory elements have a different expansion coefficient, and the difference is about 17%. So this is not so easy to handle and to manufacture such thermocouples. But obviously it is possible. Only a limited number of sheath materials are suitable to withstand process environments usually present at high temperatures of 1,500 degrees and above. So 1,500 degrees and above environment means all molten metals are accepted. Temperature measurement, inside temperature measurement in molten metals is a completely different theme. We need minimum 1 day to cover all the aspects for doing this. Molten metals are extremely aggressive. Extremely. And it is not easy to do quite precise immersion measurements with thermocouples in molten metal. Even not at lower temperatures like lead or tin or zinc, which are quite reasonable temperatures. Even aluminium, 660 degrees, is not really a high temperature. but molten aluminium is extremely aggressive to steel protection tubes. So this is not possible. Okay. So insulation material, magnesium oxide or hafnium oxide is recommended for such applications. They have good insulation numbers at higher temperatures. Beryllium oxide would be better, but beryllium oxide is not allowed in all countries of this world, because when you have particles below 5 microns in size, you can have them in your lung, and beryllium oxide inside your lung is hazardous because of cancer. So mostly it is protected. So magnesium oxide or even hafnium oxide is recommended for such applications. Both have not any effect on your body. You can eat it, it's no problem. It comes out as it is, even in white. So the sheath materials depend on what is the permitted atmosphere. And you see that the noble metal sheath materials are only for oxidizing and inert or vacuum applications, where pure platinum sheath is not possible in vacuum applications. The partial pressure of platinum is quite high, and so the temperature in the vacuum furnace may be above the partial pressure temperature, and so the platinum disappears. Yes, so mostly alloys are used. Tantal is ideal for use if there is a fear of metals, even molten metals, in the atmosphere, because tantalum from most molten metals could not be covered. When you put out the tantalum sheath, there is no metal on it any longer. But again, molten metals are extremely aggressive, and they also have an effect on the tantalum. Tantalum cannot be used in reducing atmospheres. It is not possible. Under certain conditions of pressure and temperature, tantalum hydride is formed, a combination of tantalum and hydrogen, and tantalum hydride is a gas. So molybdenum is the only solution for reducing atmospheres. Molybdenum sheath and tungsten rhenium thermocouples are the only solutions. Okay, this is an imagine of such a high temperature thermocouple. The brass head over there, this is the interface between the atmosphere and the inner construction of the thermocouple. The lower left corner is the welding between the molybdenum sheath and the stainless steel supporting tube. Cables, two types of cables are mainly available: extension cables. They use the same material with the same characteristics as the thermocouple itself, and compensating cable. They use similar material with similar characteristics to the thermocouple. Both are maybe used only in a limited temperature range, mostly depending on the insulation material. You can imagine that, for example, a PVC insulated cable may not be used above 100 degrees centigrade, while a Teflon insulated cable may be used up to 250 degrees centigrade, or other materials like Kapton even higher. They are also available in class 1 and class 2. And you see that class 1 extension cable is only possible for the non-noble metal thermocouples. Noble metal thermocouples, because of the price of the noble metal, does not allow to make cables from it. These cables are only available in class 2. And they are nominated with a C before the letter for after the letter for the type of the thermocouples, and the third letter A and B classifies a different temperature range.
Just want to have a difference to be known. Where I should use extension cable and where should I use the compensation?
You have a look in the 50584. There is mentioned that a thermocouple class 1 with a compensating cable class 2 does not necessarily form a class 1 sensor. So if you like to have a class 1 sensor, you chose a thermocouple class 1 and a extension cable class 1. Then you are quite sure that your complete system complies with class 1. Only then. The difference in price between compensating cable and extension cable now is really small, because the use of extension cable increases, so the production quantity increases, and this means that the price decreases. There is really, in most cases, only a difference of a few rupees. This. And on the other side, it gives you much more advantage in terms of uncertainty. Sorry?
Yeah.
Yes?
In terms of accuracy or
Yes. Accuracy and reliability, of course. Interchangeability. Yes, you have thermocouples in stock, and accidentally you need one, you take it and put it in, and you are sure that it has the same properties. Yes. So there are a lot of advantages, and I can only recommend, don't buy a thermocouple with compensating cable. Don't do it. It causes only problems, internal problems, stock keeping, lists, training of the people, and so on and so on. It costs a lot of money internally. Yes? Okay. Purchasing manager looks only what is on the bill. So this is the natural difference between purchasing and technical. Okay. You see? So the different insulation materials are suitable for different temperatures, ambient temperatures, and ambient conditions. Yes? PVC in Europe is nearly prohibited because of some ingredients in the standard PVC which is accounted to form cancer. So the content is limited. Finally, my previous company, we did not have it any longer in stock. PVC material we did not buy, and we did not sell to customers. Because of the decreasing production quantity for this kind of cables, especially in Europe, the price increased rapidly, and there was nearly no difference to other insulation materials, so it makes it not useful to take it in stock. Yes? Silicon is a good idea, always. It is stable, for example, against sunlight, as well as Teflon is stable against sunlight. Rubber is not stable against sunlight. You cannot use it in free air installations. You should not use it. And especially the resistance against acids and gasoline and diesel and other hydrocarbons are the limiting factor what you use. And among this, the Teflon material is the most common, and so the demand, I think the demand for Tempsens is somewhat around 300, 400 kilometers a year for Teflon cable. Yes, and all other types of cable are far below this quantity. Yes.
Actually, still a lot of PVC cable is used in India. Most of the cable which is armored cable is PVC.
In Europe, this is not longer allowed. Okay. This is a cross-sectional view of a mineral insulated cable. On the outside, you have a metal sheath. For non-noble metal thermocouple, it is either Inconel or a stainless steel. Seldom other materials. And inside you have 2 or even 4 wires of thermocouple material, and the rest of the inner diameter is filled normally with magnesium oxide. 90% of the mineral cable is filled with magnesium oxide. And due to the production process, when the production for a mineral insulated cable starts, the outside diameter of the pipe is about 1 inch. Yes? And the 2 thermocouple wires are in the size of 4.5 to 6 millimeters, nearly the size of my fingers. And the blocks for the insulation material is normally 4-inch long, 100 millimeters approximately, with 2 or 4 holes, and you feed the wire into the holes and then the entire system into the pipe. Pipes are 6 meters, normally 6 meters, or 6.5 meters. Yes, and then the production process starts. First in rollers to reduce the diameter up to 10 millimeters, and then you draw it through what is called stones.
Yeah, through the die.
Yes, through the die, yes. In Europe they are called stones. Okay, up to the desired millimeter. If it is 8 millimeter or 6 millimeter in diameter, even 4.5. If you like to have smaller diameters, you do not start normally with 1 inch outside diameter. Normally you start with 1/2 inch pipe or 3/4 of an inch pipe. And then you can draw it down up to 0.25 millimeters outside diameter with 2 insulated wires inside. And when you look on the dimensions in the right table, the conductor diameter is somewhat around 15% of the outside diameter. So if the outside diameter is in the size of your hair, then you can consider what is the diameter of the inner thermocouple wire. And so anyway, you need a microscope to handle such a thermocouple. When you count all this together, you will find that it is only 75%. Only 75% of all dimensions are included in a standard. So 25% is vendor specific. For example, material from Japan, Okazaki, the distance between the thermocouple wire and the outer sheath is smaller than in the inside. So the advantage is at high temperatures, the insulation resistance between the two wires is higher. The disadvantage, the insulation resistance between the sheath and the thermocouple is lower. Yes. ABB example for in Germany, they have quite thick sheath material and thermocouple wire, while the insulation is really at the only 8%. Yes, so this material is the manufacturer, mostly women which connect it, they like this material because it does not break. The welder itself does not like the material because it forms a thick tip, and so he has a problem with the insulation resistance. So not everything is ideal, and so we had about 4, 5 different vendors for the mineral cable, even for type K, with different characteristics, and we selected the material according to the application if we had a good knowledge for the application, of course. The tip, as a standard, is insulated from the sheath. Only on special request, the thermocouple material is welded to the outer protection tube. This system has a lower response time, 15 to 25%. But the disadvantage is that your measuring cycle is connected to the local ground, and the local ground potential is not necessarily the same as in your central control room. So you need a meter with a very good insulated input against mains and ground. Mainly you have what is called a floating ground, but this makes it not ideal for precise measurements. So normally, and most of the vendors say, when you do not make any mention in your order, then it is always insulated thermocouple. The dimensions for the thermocouples in the case of being insulated are also in a standard, in an international standard. And so you have also other possibilities for your tip with outside the sheath or inside, or it depends on the application and on the required response time and whatever. The second from right is, for example, quite ideal for using the temperature in air streams. For example, car manufacturers use it to measure the temperature during a test ride. Okay, not any sheath diameter is suitable for any temperature. The lower sheath diameter are only suitable for lower temperature. This is mostly because of the insulation resistance. The response time. Response time is always a good idea to have a look on it. The response time is a direct function from the mass. Yes, obviously. 1 kilogram to heat up 1 kilogram takes more time than to heat up 100 grams to the same temperature. Everybody knows it by its own experience. Yes, 2 liters of water on your oven takes a longer time than 1 liter, obviously. Yes. So grounded thermocouples are 20 to 30% faster in the response time. This is a short table about the response time in water and air. To consider other conditions unless water and air, ambient air, you have to use correction factors. There are tables available for correction factors. And you see, for example, in an airflow, an 8 millimeter thermocouples in an airflow of 2 meters per second for a 90% step takes about 6 minutes. And 90% means you have a step from 0 to 100%, and you measure the time where the output of the thermocouple reaches 90% of the desired final value. This means 50% accordingly. Yes? And when you look for 6 millimeter thermocouple, 200 seconds, plus your protection tube. And when you have a standardized protection tube in a power station, you may consider that your response time is somewhat around between 8 and 10 minutes for temperature changes. Yes? Okay. Immersion length. The immersion length is defined as the length in contact with the medium. In real technical equipment, it is not in any case possible to realize the recommended immersion length. The best example is if you have a standardized thermowell for steam applications, then your tip is somewhat around 60 millimeters long, and inside you have probably a resistance thermometer where the sensing element is 25 millimeters long. You cannot expect that you have a real precise measurement. It is not possible. The immersion length is too low. The quantitative amount of this error is depending on the individual mounting arrangement, the construction of the sensor, the thermowell, the medium, and some others, and may not only be estimated. So the recommended medium immersion length is, as you see, somewhere around, for gases, 20 times the outside diameter, and for liquids it may be even shorter. But any immersion length below 10 times of the outside diameter, you must take in consideration a remarkable error due to the heat dissipation from the measuring tip. And it is the same for thermocouples and for RTDs. And for RTDs, normally to the minimum recommended immersion length, you have to add the length of the sensing element. So for RTDs, essentially, you need a more immersion depth than for thermocouples. Protection tubes, the same. In atmospheric ovens or furnaces, and you have a 22 millimeter protection tube, 20 times means 400 millimeters. 450 millimeters is the minimum immersion length you need. All below gives you error. And you have to take in consideration and to estimate what is the error. Okay. You see, for atmospheric furnaces at 22 millimeter protection tube, the minimum recommended immersion length is 450 millimeters. You can estimate the approximate error due to the heat dissipation by using this graph. The vertical axis is logarithmic, while the horizontal axis is linear. And when you follow, for example, the green line, you have an outside relation to the immersion depth of approximately 9. You go up vertical to the red line and then horizontal to the scale, and you found that your estimated error due to heat dissipation is somewhere near to 0.1%. When you can consider a error due to the transport of heat energy to the outside world of 1%, you can follow the yellow line to the red line, go down, and you find that somewhere around 5 times the outside diameter may be then, in this case, acceptable, or vice versa. 5 times outside diameter produce an error of somewhat around 1%. 1% at 1,000 degrees is only 10 degrees, so it's just 2.5 times outside class 1. Nothing else. Okay. We overtake this. Short, give me 5 minutes for drift. Temperature sensors are subject to operational inevitable deterioration during its conventional operation. Only when you take the sensor, you put it in your writing table and never use it, it will have an independent life. No drift, even not in centuries. But as long as you use it, it will alter, definitely. And there is no case thinkable to prohibit this. When you use it, you will alter it. As higher the temperature, as longer the time, the drift or the deterioration of the sensor increases. Anyway, unaffected if it is an RTD or if it is a thermocouple. It's for both the same. The parameters influencing the drift is different for thermocouples and RTDs, but temperature and time and the changing rate of the temperature are the main factors. And for thermocouples, even at higher temperatures, contamination because of the process atmosphere. This is a graph where, for example, the EMF is generated. The EMF is generated only in the zone where the temperature changes. Only there. Before, in the constant level at 1,000 degrees and behind the constant level at ambient temperature, no EMF is generated because there is no temperature difference. Okay? And unfortunately, for especially type K thermocouples, in this area between 350 and 650 degrees, the crystalline structure of the nickel-chromium lag and the nickel lag change. And changes in the crystalline structure from the thermoelectric side is not the same material. So it causes a mistake. As long as the position inside the furnace is not changed, and so the gradient is nearly the same, nothing happens. But when you change the position, then this inhomogeneous area comes out or in a different position of your gradient, and this causes an error. And this is in literature named the short-range ordering effect. It is the highest factor at thermocouples type K, but also noble metal thermocouples have this effect. Any 2 or more component alloy has this effect. Definitely. Okay? So this comes to the consideration in the AMS 2750. This is the automotive specifications for heat treatment. And it is based on the SAA 1450, I think, recommendation for heat treatment in aircraft applications. And this definitely states that a thermocouple type K is not allowed for recalibration. Once, and you calibrate only the start of the ring and the end of the ring, if the ring is not longer than 1,000 feet. Yes, otherwise you have to divide it. Yes, and so these samples cannot be used. So basically a calibrated thermocouple, when you calibrate it at the vendor, it is basically useless for you. Because when you calibrate it, you automatically alter the sensor. And the profile in your calibration furnace is definitely different from the profile in your process. So the only solution is to have a charge protocol. Yes? So you can take in consideration that in this ring the material is homogeneous. Okay. This is a green colored ceramic isolation. This is selective chrome oxidization. It's preferable in nickel chromium alloys under low oxygen or under carbon monoxide conditions. And the reducing produces water inside the mineral insulated cable by reducing the magnesium oxide to magnesium and water. And this causes this effect. Yeah, contamination is also always a theme. Contamination from the process atmosphere or the process conditions to the thermocouple. All thermocouples are sensitive to it. Noble metal thermocouples more than non-noble metal thermocouples. Even in the range of some ppm, impurities may produce immense discrepancies from the tabular values of the standard. The sources of impurities may be metallic sheaths, protection tube, thermowells, insulation ceramic, process. Drift of pure metals like iron, copper, and platinum is caused by diffusion of metallic atoms. Strong platinum contaminations are silicon and phosphorus, a little bit also sulfur. Platinum thermocouples are sensitive to rhodium diffusion because rhodium has a higher partial pressure than platinum. So it goes earlier into the gaseous phase and is better movable than the platinum. Binary alloys tend to initial drift due to healing of lattice defects, of course. Type K to comparative low drift due to impurities because both legs drift in the same direction. Both legs have the majority nickel, and so due to impurities they drift in the same direction. Okay, finally, there are some advantages of thermocouples against RTDs. So anybody or any user of thermocouples must take in consideration what is ideal for my process. Vendor cannot give you a recommendation. You are the owner of the process, and according to your quality manual, you have to take in consideration what sensor do we need and use, and cost and maintenance and reliability and so on, all these factors. Okay. Thank you very much.